In our next condensation reaction, we're going to be using enamines as an equivalent to enolates. So before we get into the next set of reactions, let's review how enamines are formed. So you might recall that enamines are typically made by taking a secondary amine, and in this case we're using a cyclic one, but it doesn't have to be. So as long as it's a secondary amine, and we're going to mix that with a ketone or an aldehyde to form an enamine. So an enamine you can recognize by the fact that there's a double bond, and on one of those carbons you have a bond to an amine. So this reaction is reversible, and if you might recall, if we add water and acid to the enamine, we can go back to the ketone and amine that we used to make it. The amines are always going to be secondary amines whenever we make an enamine. Are very similar in their reactivity to enolates and enols. So we can draw an enol here as well, which actually looks a little bit more like an enamine. But in whichever one of these we look at, we notice that the alpha carbon is always nucleophilic. So here's the enolate of a typical ketone, which has two resonance structures. So again, a ketone, if you add base, you can form an enolate. And then the enolate, we can draw two resonance forms of it. So one has a negative charge on the oxygen, like shown with this structure on the left. The other resonance structure has a negative charge on the carbon. For enamines, if we push electrons from the nitrogen towards the alpha carbon, we will have a resonance form that has a negative charge on that alpha carbon. So just like enolates, the alpha carbon is nucleophilic. Enols, as we've seen in the past as well, they're nucleophilic at the alpha carbon. So we could draw another resonance structure similar to what we did with enamines, which has a negative charge on this alpha carbon. We have now a double bond here, an oxygen with a hydrogen. So this is the reason why enols, enolates, and enamines are sort of lumped together. They all have a structure that is typically made from a carbonyl compound, and it makes that compound nucleophilic at the alpha carbon. Due to the similarities in reactivity between enamines and enolates and enols, enamines can do similar reactions as both enolates and enols. In other words, for example, we can do alkylation reactions at the alpha carbon. So if you have an enamine as shown on this slide here on the top, if we add an alkylating agent, we can add an ethyl group to the alpha carbon, which would be this one here. If we follow the reaction with aqueous acid, we can convert the intermediate of this enamine into a carbonyl compound. The reason for that is, remember, the formation of enamines is a reversible reaction. So if we add aqueous acid, we could go back to the original, or go back to a ketone or an aldehyde plus a secondary amine, which is what we did here. So in this example, we made a bond between the alpha carbon, which is this one here. So this is the alpha carbon of the enamine. And we made a bond to the ethyl group of the alkylating agent. So that carbon there would be this carbon here. And then the enamine, nitrogen, gets hydrolyzed into this ketone. And then we also have an amine byproduct. This next example will probably make it a little bit clearer of exactly what's going on here. So if you have an enamine and you add an alkylating agent like this alkyl halide, the enamine will push electrons towards the alpha carbon, which will then attack the carbon with the leaving group. That forms this intermediate. So we have just formed this bond here between the alpha carbon, this one, and the carbon that had the leaving group. And what happens to the nitrogen is it forms an iminium ion, which we see here. So as it pushes electrons towards the alpha carbon, it forms that double bond, a positive charge on the nitrogen. And iminium ions will be hydrolyzed by aqueous acid into a ketone and a secondary amine. Enamines will do all sorts of reactions that relate to what enolates and enols do. For example, they can do reactions very similar to the Michael reaction. When it comes to using an enamine, we're essentially replacing the enolate with an enamine in the Michael reaction. And we often refer to an enamine Michael reaction as the Stork reaction. So here's an example. If we start off with cyclohexanone and we add this cyclic secondary amine, we will form the enamine that you see here. So the nitrogen attaches where the carbonyl is, you get an enamine out of it. Then that enamine basically behaves like an enolate, so is nucleophilic at the alpha carbon, which is this one. That alpha carbon will attack the beta carbon of an alpha beta unsaturated carbonyl. That leads to this intermediate. So we just formed this bond here. Notice the nitrogen of the enamine becomes an iminium ion. We form an enolate here at the alpha carbon. When we add aqueous acid in the second step or the last step, it's actually the third step of this reaction. When we add water in this last step, we're gonna do a few things. Number one, we're gonna protonate the carbon. So this carbon here will be protonated and it will become just a regular carbonyl. The iminium ion will be hydrolyzed into a carbonyl and a secondary amine. Here's another example of the Stork reaction, which again is a Michael reaction using an enamine instead of an enolate. So if we start off with an enamine, the nitrogen again will push electrons towards the alpha carbon, which will make that carbon nucleophilic. That alpha carbon will attack the beta carbon of an alpha beta unsaturated compound, such as a ketone. We now form, in this reaction, this bond here is reacting the alpha carbon of the enamine with the beta carbon of an alpha beta unsaturated carbonyl. Initially, we're going to have an enolate, and I'm showing here one resonance form, but we could have another resonance form that looks like this, where we have a carbonyl and a negative charge here at the alpha carbon. And you could draw out the rest of the structure if you want, but something like this. So we have the methyl, etc. Okay, that enolate, whether you use this resonance form or this resonance form, is going to get protonated and it's going to become the ketone that you see in the product. The iminium ion here will be hydrolyzed into a ketone, and you're going to get a secondary amine as a product, as a side product. Here's an example of an enamine participating in the aldo reaction as an equivalent to a enolate. If we use this example involving an enamine and we add it to a ketone, this alpha carbon should add to the carbonyl carbon of the ketone. So we would get a reaction between this carbon and this carbon. As a result, this carbonyl, this ketone, becomes an alcohol initially, which you see here in the product. We're forming this bond here between the alpha carbon on the left side of that line and the carbonyl carbon on the right side of that line. Then when we add aqueous acid, the iminium ion that forms from this nitrogen will become a carbonyl, and then we'll get a side product of a secondary amine. The secondary amine should always can be determined based on what you have here in the enamine. So simply that nitrogen will be replaced by water, and it picks up a proton to become the secondary amine. Here's another example involving the mechanism as well to clarify how this reaction occurs. So the nitrogen of the amine will push electrons from the alpha carbon and attack an aldehyde. That initially gives you this intermediate shown here, and then the oxygen picks up a proton from aqueous acid. In addition, this iminium ion becomes hydrolyzed by the aqueous acid to form a ketone. And we get a side product of a secondary amine. Again, notice this secondary amine is related to the nitrogen that we have in the enamine. The nitrogen picks up a proton to become that secondary amine. Many examples of biological aldo reactions involving carbohydrates. Here's an example using this ketone reacting with the amino group on an enzyme, an aldolase enzyme, which will form an enamine. So if you see here, we have a carbon-carbon double bond and a nitrogen attached. That enamine can react like other enamines we have seen in this chapter through the alpha carbon, which will be this one, to attack an aldehyde and essentially do an aldo reaction. So in the process, we're going to be forming this bond here. Notice the aldehyde becomes an alcohol, so that refers to this aldehyde. And then the enamine, the alpha carbon of the enamine, will be this one here. Addition of water will hydrolyze the iminium ion. So this iminium ion intermediate will be hydrolyzed into a ketone, which we see here in fructose. Here's another example of an aldo reaction from a biological system, this time involving type 2 aldolases, which are typically found in fungi and bacteria. It starts off with this ketone, which is converted into an enol. So that happens by base removing the alpha hydrogen, and then the carbonyl get protonated, forming an enol. The alpha carbon of this enol is nucleophilic, and so it would add to an aldehyde. The aldehyde oxygen gets protonated to become an alcohol, this alcohol here. In this reaction, we're forming this bond. This is the alpha carbon of the enol that we use in the aldo reaction. And as a result, this is a way to make fructose. In this reaction, we want to use an enamine to prepare the following compound. When you look at this compound, one thing you should notice is that we have a nitrile, and the carbon of the nitrile is 1,5 to the other carbonyl in this product. So this is a sign that we're doing a Michael reaction. We are likely forming this bond in this Michael reaction. And again, you want to use an enamine as the Michael donor. Looking at the product from this reaction, this one here, as we recognize or discussed in a moment ago, this is a 1,5 dicarbonyl compound. So if we consider the nitrile carbonyl, it will be 1,5 to the ketone. And that's perfectly set up for a Michael reaction that will lead to forming this bond. If we want to use an enamine, enamines are typically made by taking a secondary amine and mixing it with a ketone or an aldehyde. So the ketone to the left of this bond that I just drew, or this line that I just drew, would be used or mixed with a secondary amine to form an enamine. So for example, we would use this ketone and we could use this secondary amine. It doesn't necessarily have to be that one or even a cyclic one, but that's just the example we're going to use. When these two combine, we should get an enamine that looks like this. And then if we add an alpha beta unsaturated nitrile, so that would allow the nitrile to be the Michael acceptor, the alpha carbon of this enamine would add to the beta carbon of the alpha beta unsaturated nitrile, forming this bond here. The alpha carbon of the nitrile would be present now containing a negative charge. When we add aqueous acid, that carbon gets protonated and it becomes simply a carbon that has two hydrogens in the product. The iminium ion gets hydrolyzed by aqueous acid into a ketone, which we see in the product, and a secondary amine. In this question, we're going to use an enamine reaction to prepare the following compound. If you notice, this product of a enamine reaction has a 1,5-dicarbonyl. So typically, that's a hint that we're going to be using some sort of microreaction. If we're involving enamines, as we discussed earlier, is called a Stork reaction. So this is a Stork reaction, and we want to make the following bond here. So if we draw a line, we're referring to making that bond there. On the left side, we're going to be using, since the question asks us to use an enamine, we're going to use an enamine from this ketone. So if we use that ketone and add a secondary amine, again, it doesn't have to be this particular secondary amine, but any will do. We would make an enamine that we see here. And if we add that to an alpha beta unsaturated ketone, we can make the product that is part of this question. So this alpha carbon will attack the beta carbon. We get rid of this double bond. We're forming this bond between the alpha carbon of the ketone, the beta carbon of the alpha beta unsaturated carbonyl. Notice that beta carbon also has a methyl group, so that's the methyl group sticking up. And then if we continue to count down, beta carbon is attached to the alpha carbon, so this is the beta carbon, this is the alpha carbon. Then we have the ketone and then a methyl group.